So we're still in section 5.3. We're finally finishing it up though. Today we're going to talk about concavity. Did you talk about concavity last year? Okay, so you know basically graphically what concavity means. Okay, what you don't know is the definition of concavity. Okay, just because it's not appropriate to teach that in pre-cal because you don't know about derivatives yet. So the definition is this: the graph of a differentiable function y equals f of x is concave up on an interval I if f prime of x is increasing on I, and concave down on an open interval I if f prime is decreasing on that interval I. By the way, I is an open interval. It says that in here, but I'm writing it again because we've been pounding that increasing and decreasing for a function is on a closed interval. Concave up and concave down are on open intervals. So graphically, what this looks like, and this is probably something you did, is that in this region, my function is concave down because the derivative, which is the slope of the tangent line, goes from positive to 0 to negative, right? The derivative is decreasing. And then over here, someplace we have a change, and over here the derivative is negative, now it's near the 0, now it's positive, the derivative is increasing. So the function is concave up. One of the things you have to be really careful about is, okay, I can't say the function or it unless there's only one function in the whole thing. If you're also talking about a derivative, well, the derivative is a function also. So you can call it the original function, or better still, call it by whatever its name is. Notice that all of the tangent lines here lie on or above the graph. And for this region, all of the tangent lines lie below the graph. So one of the things that this means is that a linear approximation of f of x will be an over approximation. Right? If we use the tangent line, like we've done before, write the equation of the tangent line, and then we use it to approximate something. Well, if we use it to approximate the value of the function, my approximation is going to be too high if the function is concave down. Over here, a linear approximation will be an under approximation. Because if I use this tangent line to approximate the value of the function at this point, well, my tangent line is going to be underneath the curve. Questions like that will occasionally come up on the AP exam where they'll ask you to do a linear approximation, and then they'll say, is this an over approximation or an under approximation? And it's just based on the concavity. It doesn't matter whether the function is increasing or decreasing, it just matters whether it's concave up or concave down. All right, and this is just what we've said just a second ago. So let's go on to page 2. A point on the graph of a function where the graph has a tangent line and where the graph changes concavity is called a point of inflection. So back up to here. This point right here is a point of inflection. If you were to lightly put your pencil on this and trace the curve, your hand will feel it when you change from concave down to concave up. It doesn't matter whether you're right-handed or left-handed. I used to worry about that, but it doesn't make any difference. When you're drawing it, you feel your wrist kind of move from an overhand motion to an underhand motion, right? That's the point of inflection. And notice that this is the steepest part of f of x in this neighborhood. All right, not the steepest part, forever, but in this neighborhood, that's the steepest part. That's where your point of inflection is. Now, accurately finding a point of inflection just by looking at a graph, very difficult, because what happens is this gets very line-like right here. Right, and so if you zoom in on this, it looks a lot like a line, and you're like, I can't really tell where it switches from an overhand motion to an underhand motion. So, how are we going to determine this? Well, we look at the second derivative. If f double prime is greater than 0 on an interval, so when the derivative of something is positive, that means that the function that it's the derivative of, in this case, f prime, is increasing. And then by definition, f is concave up. Yes, it's another layer deeper. Likewise, if f double prime is less than 0 on an interval, then f prime is decreasing on that interval. So a point of inflection of the graph of f is between intervals where f prime changes sign. One of the things that happens on this is students start just looking for where f double prime is 0, which is a good start, but it's not enough. You have to check, does the second derivative actually change signs? It's possible that it will not. All right, let's take a look at this one. Let's let f of x be 1/5 x to the 5th minus x to the 4th plus 3. Find the x-coordinate of each local extreme value and identify the type justifying your answers. Okie dokie. So if I'm trying to find local extremes, I want to find where my function changes from increasing to decreasing or decreasing to increasing. So we'll take the derivative to find critical points. So that's going to be x to the 4th minus 4x cubed. I always encourage people to look for places where that doesn't exist first. It's a polynomial, so it exists everywhere. So I'll move on to finding the critical points by setting that equal to 0. So to do that, I'll factor out an x cubed. So that's that x is equal to 0 and x is equal to 4. So a number line can be helpful. Again, it is not justification, but it kind of helps you see what's going on. If I pick a number less than 0 and substitute it into the derivative. And again, it's always easier if it is in factored form to substitute it into the factored form. So, -1 cubed is -1, -1 minus 4, -5. Negative times a negative is positive. So here f prime is greater than 0, which tells you what about f?
It's increasing.
Yeah, f is increasing. Between 0 and 4, say +1, that'll be 1 times -3. That's negative, so f prime less than 0 means that f is decreasing. And at 4, if I pick a value larger than 4 and substitute it in, x cubed and x minus 4 are both positive. F prime is positive here, so that means that f is increasing. So our local extremes are, first of all, at x equals 0, f has a local max. Because how do we know that? Well, what changes? Don't say it.
F prime changes from, or F changes from increasing to increasing.
So that's true, but we have to base it on, we've tested the derivative. We haven't ever actually looked at the function itself. So f prime changes from positive to negative. And if you wanted to go on and clarify that, it's not a bad idea, but it's not required, so that f changes from increasing to decreasing. Okay, I kind of like that. What?
It just looked like you were trying really hard to finish that word and you just quit.
I
know that you were trying to abbreviate it, but it just looked like...
I'm really struggling with the pen today. It's not happy with me. All right, then at x is 4, f has what? Yeah, local minimum. Because f prime changes from negative to positive. So f changes from decreasing to increasing. So far, so good? All right. So now they want us to find each point of inflection. So a point of inflection is where the graph has a derivative that changes from increasing to decreasing or decreasing to increasing. I have the derivative, so I need to take the derivative of the derivative and apply the same rules that I did here. So I'll take the second derivative, f double prime of x, which will be equal to 4x cubed minus 12x squared and find where that's equal to 0. I can factor a 4x squared out of both of those. So x equals 0 and x equals 3. So we're going to see where f double prime is positive and negative. So I've got 0 here and 3 here. If I pick a negative number and substitute in, the 4x squared is going to be positive. The 3 minus x will be negative. So here, f double prime is negative, which tells me what? Yeah, f prime is decreasing. Which is the definition of f being what? Concave down. See how it's just one more layer? Between 0 and 3, if I choose 1, I've got a positive and a negative. No, so here f double prime doesn't change sign. F double prime's negative, which means f prime is decreasing, which means that f is concave down still. If I pick a value larger than 3, say 4, the 4x squared is going to be positive. The 4 minus 3 also positive. Here, f double prime is positive, which means that f prime is increasing, which is the definition of concave up. So f is concave up. So I have a point of inflection on the graph of f. Come on. Maybe it'll do better if I get up there. Wow. I thought it was maybe how I was holding the pen or something, but it doesn't appear to be. At x equals 3. So as I said earlier, one of the things that you're likely to be asked on the AP exam is you'll be given the graph of the derivative of a function, given some information about the original function, usually that it's continuous, and then asked questions about the function. So let's take a look at this. I'm going to switch that to that. Okay. So, on what intervals is f increasing? Well, f is going to be increasing when its derivative is positive, right? The derivative is positive through here, 0 at -1, but that actually doesn't trouble us at all because it's just for that one point, then positive again until we get to here. So that's going to be on the open at -infinity, because we never reach -infinity, closed at 1. And on the closed at 4, but open at infinity. All right, Next question. On what intervals is f concave up? By definition, what does it mean for a function to be concave up?
Its derivative has to be greater than 0.
No.
On
Well, greater than 0 and positive are the same thing.
Has to be increasing.
Has to be increasing. Right? The definition of concave up is where the derivative of the function is increasing. Okay, where is this function increasing? Well, from -1 to 0. And then from 3 to looks like infinity, unless there's some other weird thing going on. Again, for concave up and concave down, our intervals are always open. All right, let's find this. Find the x-coordinate of each local extreme value of f and classify each. All right, so when we're looking for extreme values, we first try to find critical points, right? Critical points are where the derivative is either 0 or doesn't exist. Well, where are those points? Yeah, -1, 1, and 4. At -1, my derivative goes from positive to positive again. So the function goes from increasing to increasing some more. So do I have a local extreme value there? No. On the AP exam, normally what they'll do is they'll say, find each critical point of f, which would be what you guys said, the -4, or excuse me, the -1, the 1, and the 4, right? And then it would say classify each as a local maximum, local minimum, or neither. So if they had asked the question that way, we would have said, well, at x is equal to -1, there's neither a local minimum nor a local maximum because the derivative doesn't change signs. So what do we have on the graph of f at x equals 1? A local maximum. And what about at x is equal to 4? A local minimum. All right. Now, they want you to find the x-coordinate of each point of inflection of the graph of f. All right. So, as I'm going from here to here, is f prime increasing or f prime decreasing? Decreasing, which means that f is doing what? It's concave down, right? And then here to here, f prime is increasing, which means f is concave up. So this is the location of a point of inflection. So x equals -1. All right? From 0 until I get to 3, f prime is doing what? Decreasing. So f is concave down. And then here, f prime is increasing. So f is concave up. So that's another point of inflection. Oh, I left one off. What about at 0? F prime goes from increasing, so f is concave up, to f prime is decreasing, So concave down, so I apologize. I left that one off. Do you remember how a minute ago I said when you look at the point of inflection, it's where the graph is steepest, right? So steepness is measured by the derivative, yes?
Yes.
So where you have maximums and minimums on the graph of f prime is where you're going to have points of inflection on the graph of f. Because f prime measures steepness. I'm sorry? No. The tangent line to this is going to be horizontal, but on the original function it's not. On the original function, this is going to be the steepest point in this neighborhood. This will be the steepest place in this neighborhood and the steepest place in this neighborhood. Yeah. All right, we're not going to try and graph it. That's for another day. All right. Pardon?
Ever do it. We don't have to ever do it. It's good.
Yeah, we'll probably do it at some point, but we'll actually learn some more stuff that'll make it easier. All right. We have the first derivative test for local extrema, which says that if f prime changes from positive to negative, f has a local maximum, and if f prime changes from negative to positive, f has a local minimum. There is also a second derivative test for local extrema. This is not the second derivative test. Yes, we are using the second derivative, but it's not the second derivative test. The second derivative test isn't about finding points of inflection. Students occasionally want to make, they conflate the two. The second derivative test for local extrema says this: if f prime of c is 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. Well, let's think about that. If f prime at a particular point is equal to 0, then if you were on the graph of f, you would notice that it had a horizontal tangent, right? And if f double prime is less than 0, what does that mean about f? If f double prime is less than 0, that means f prime is doing what? Decreasing, which means f is concave down. Oh, hey, if I have a function that's concave down at this point and it has a horizontal tangent, that's got to be a local maximum. Okay? And vice versa, still having a horizontal tangent, but now we have f double prime as positive, which means that f prime is increasing, which means the function is concave up. You're going to have a local minimum at that point. The question comes up, well, when do we need to use this? The answer is when it tells you to, which isn't going to happen on the AP exam. They're not going to say, use the second derivative test, I don't think. There's always a possibility they could do that. The other time that you do it is when you know these things about the first and second derivative, but you don't actually know the function itself. And that does happen on the AP exam. Well, they'll give you information about it. They don't actually give you the function, so you can't even put it into the calculator to look. So let's take a look at this. Use the second derivative test to classify each extreme value of f of x is x cubed minus 12x minus 5. So I'll take the first derivative. And it starts off just like I'm doing the first derivative test. I take the first derivative. I look for critical points. There's no place where the derivative doesn't exist, so I'll just look for where it's equal to 0. That's just 3 times x squared minus 4. So my critical points are x equals plus or minus 2. Okay, so it starts off exactly like the first derivative test. But instead of doing a number line and looking to see what the signs are of the first derivative on each side of plus or minus 2, what we're going to do is take the second derivative, which is 6x, and evaluate the second derivative at all the critical points. So f double prime at -2 is -12, which is less than 0. Therefore, f has a local what? Maximum. Because the second derivative being negative means that the function is concave down there. So my tangent line's got to be above it, so that's got to be a maximum. On the other hand, f double prime of 2 is positive 12. That's greater than 0. Therefore, f has a local minimum. Okay. I'm going to give you something that summarizes the stuff that we have learned in terms of what does a derivative tell us about a function.
You're welcome.
I'm getting apart. And let me pull that up. So this is kind of everything in a one-page summary. Okay, so we'll just go over it real quickly. On the back, there's an example, and it talks about all the different stuff. We won't go over that together. So, first of all, a continuous function will have a maximum and a minimum value on a closed interval. That's the extreme value theorem. They can only occur at critical points, which is where the derivative is 0 or does not exist, or at endpoints of the interval. That's the candidate's test. If f prime is positive on an interval, then f is increasing on that interval. If f prime is negative on an interval, then f is decreasing on that interval. Everything else is an extension of that idea. So here we have the first derivative test. If f prime changes from positive to negative at x equals c, f has a local maximum at x equals c. By the way, this assumes that the function exists at c. All right, I was trying to make this as compact as possible, and it's pretty long already. If, on the other hand, f prime changes from negative to positive at x equals c, then f has a local minimum at x equals c. Here's what we did today. Definitions of concave up and concave down. So a function is concave up on an interval if and only if f prime is increasing on that interval, and concave down on an interval if and only if prime is decreasing on that interval. Therefore, if f double prime is positive on an interval, f prime is increasing, right? That's just one level up from that. That means it's going to be increasing, and then go another level. Now we know that f is concave up. And the same for concave down. A point of inflection is where there is a tangent line and the concavity changes. Therefore, if f double prime changes sign at a point where f prime exists, then f prime changes from increasing to decreasing or decreasing to increasing, and f changes concavity and has a point of inflection. And it points out here, this point will be a local maximum or a local minimum on the graph of f, which is what we did earlier, right? And then there's the second derivative test for local extrema. So that's kind of all of it. I'm not going to take the time to go through all of this stuff, but it's not a bad idea for you to. And that's all we have for